So the given problem statement is to convert a Roman numeral to an integer. It's a Leetcode 13 question, which is an easy one. So let's get into the problem. It states that if you can look at the examples here given, it's xii gives 12, which means xii Roman numerals will convert to 12 in an integer numeral. Similarly, xxvii converts to 27 and lvii converts to 58. I'll explain what these are in the coming explanation to the particular problem statement, but the introduction is to convert a Roman numeral to an integer one. Let's get into the introduction. Now let's get into the problem statement. Here what they said is we have to convert each and every one of the Roman numerals into integer, and we have to add the particular number to get the final integer, which will convert this Roman numeral that is given into the integer. Let's look at this one. Romans used to use this particular chart to see the Roman integer relationship. It states here that I gives rise to 1, which means I is the equivalent of Roman to a 1 in integer representation. Similarly, V for 5 and all these rest of the numbers. But Romans thought that was too easy, so what they did was they introduced two more conditions for this particular statement. The first one, which is easy, being that there are four digits in Roman numeral A, B, C, D. Then the integer representation of A will be greater than B, which will be greater than C and D, and so on. So the numbers will be starting from the largest to the smallest. But the condition that makes this interesting is the fact that if sometimes we can represent B which is greater than A, then the condition would be that A and B will be the Roman integer representation of integer of B minus integer of A, which means that if A happens to be less than B, what happens is we have to subtract the value of A from the value of B in the integer representation when we are adding it to tally up the particular value of the integer. So these are the two conditions we have to look out for, which is mainly what makes this problem tricky. So now let's get to the better part of this question, which we all have been waiting for, which is the intuition. So we are given a particular Roman numeral and we have to convert it to an integer. In order to do that, we can use one method, which is, let's take an example, which is 5111 give us 8, right? So how did we get to this conclusion? We know Roman numeral is still 8, it's easy, but let's see how we got here. If we look at this one, 511 or 5II has 4 Roman numerals, 4 individual Roman numerals of a particular Roman number. If you look at the previous table that was given, we had the value of 5, V, which was 5. So, and we also had the value of I, which was 1, and the other I, which is 1, the final I, which is 1. So basically what you have to do here is just add the values. We add the individual values of 5, 1, 1 and 1, which will give us a particular value of 8, which is 8. So basically what we're doing is we're systematically going to each and every digit of the particular Roman numeral, and we're converting them into an integer using the table we have as an information. And thus, by adding all of these, we get a particular number. If we add the particular integer digits for each and every Roman numeral, gives an 8. But we have a problem here, which is anyone could have solved this problem if it was just as simple as that. But we have two conditions right there, right? So what if we have to represent 9? So what Romans do is, when you have to represent 9, instead of writing 5, 1, 1, 1, 1, instead of representing this as 9, what they do is instead they cut this thing out. And what they do is they'll represent 9 as this, which is 9, which is confusing to a lot of people. But let's get some context here. What they basically do is, for all the particular values such as 10, 5, 100, 50, 500 and 1000, and that's the values that are there in Leetcode. So what they do for all these is, rather than getting the value of 9 or 4 or 49 or 40, rather than getting the values of 4, 9, 40, 90, 400 or 900, rather than getting all these values, by representing them in the normal way which they did, they represent them as 1 and x. Let's look at this one carefully. One's integer representation or i's representation is 1 and x representation is 10. So 1 plus 10 will give us 11 usually. It's not equal to it, right? It's not equal to 11. But the problem here is, rather than, if we look at the condition given there, it's given that 1 and x will give us 9. Why? Because in the condition, if the integer value of x is greater than the integer value of this one, what they do is, rather than doing this, they'll subtract it, which will give us 9. So it gets tricky when you get in the territory of representing 9s and 4s and all these numbers, but let's not panic here. Let's look at this problem a little bit deeper. So we are basically seeing that x and I will give us 9. If you look at this, so basically rather than writing 10 and 1, it's basically 10 plus of minus 1, right? So what happened here is, we're going from back side when it comes to these kind of cases, which is, we look at the number which is 10 and we look at this which is minus 1, because x is greater than 1 and 1 is in the left side, which it shouldn't be. So 10 minus 1 gives us 9. So rather than going from the left to the right, how about we just come from the right side to the left side? We keep checking the values of each and every one, each and every digit, because we know that the rightmost value will be smaller than the left value preceding that value. So if we check at the right value, if we keep going to the left side of the values, what happens is, when we keep going to the left side values, we could just keep encountering the number which is greater than the previous number, and we can keep adding that thing. But if it is smaller than the value, the particular current value which happened here, like x and I, what we can do is subtract 1. So rather than going from the first to last, what we can do is, if we take another example which is 4, gives 4, right? So what we can do here is, rather than going from 1 and saying 1 plus 5, oh no, it's greater than 5, so minus 1, and doing that, we can do is, we can go from the back side. Yeah, 5 is greater than a particular value which we will see whether it's true or not. We'll go to 1. 5 is over 1. 1 is less than 5, right? What we'll do is plus of minus 1. You get the particular value 1. After that 1, there's nothing else. So this is the final value, which is 4. So the basic intuition is to go from the rightmost side of a particular value till you get the values to the leftmost side, and you add or subtract them depending upon the value preceding the previous one. So now let's get into the intuition code. So basically, let's look at the intuition code here. We are going to use Python and pseudocode, a mix of Python and pseudocode, to basically represent this intuition code, and the final code will be in Python. So let's start with this particular string, which is ix, which we all know is 9, but let's see how this algorithm will work for this one. We have ix, which we know is 9, but let's see how this algorithm is going to calculate this as 9. First, s is I and x is a string. It will be given as a string. So we had to return an integer, which is a sum, which we're going to take it as 0. This is going to be our main answer at the end, which we should return in Leetcode. So we're going to take three variables here, which is I, sum, and n being the length of the particular string, which in Python we use len for the length of the string. For I, we are going to use it as a pointer to point to the various Roman digits of the particular Roman numeral, and for n, we're going to use it as for sum, we're going to use it as the particular number which we should return at the end, which is the integer representation of the Roman numeral. So we initialize I to n minus 1, since for in Python we usually end a particular string at n minus 1 value or length of s minus 1, which is for I and x. The indexes of this one will be 0 and 1. So since the length of the string is 2, so 2 minus 1 will be 1, and I will be initialized to the back, as we all know, from the right side of the particular Roman numeral, and I'm going to go to the left each and every time till there are no numerals left, and the final value will be the value of a particular number. So we'll have a while loop for this one. So while I is greater than or equal to 0, we're going to sum this thing, which is as long as the value of I is reached till here, as long as the value of I is in 0 and doesn't go anywhere beyond this, we'll have an out of index range error. So as long as I is greater than or equal to 0, we'll be continuing this while loop. If we get to this sum plus equals to roadmap of s of I, which means that here we use the row map. Sum plus equals to row map of s of I. So here row map is a particular hash map, which I'm not going to write here, but we already know the table to this particular hash map. I have given it in the introduction video, or the introduction problem explanation video, in the problem explanation part of the video. So basically how we write this thing is, we'll basically write row map is equals to, we'll use brackets, flower brackets, and have 1 as, we have 1 as 1, I as 1, and v as 5, and so on. Basically this is how we represent a row map here. So what it does is, it's a hash map which will use to get the particular integer value of each and every Roman numeral. As we have seen in there, we go from left to right and we'll calculate the Roman values of the numeral value of the Roman value, now to get the integer value for each and every one of them, and we'll add or subtract them based on the particular condition. So for now we're going to add them using this map. And in this row maps, what we'll do is, we'll add sum plus equals to row map of s of I. So here if you look at it, sum is now updated to I, which is x. So we have I is in 1 currently. So x is 1, it's pointing to this particular digit, and x is, as we all know, is 10. So sum will be 10. We have the n also as 2. So the variables here are particularly I is equals to 1, sum is 10, and n is still 2. We don't need to think about n for now. Once it's initialized, it's over. So the integers the variables which are supposed to be concerned about is I is equals to 1 and sum is equals to 10. So for this one, it's 10. Now let's look at the other condition, which is if I is equals to 0, which is a condition, we have to break it. Now suppose we are in this particular stage where I is 0 and we already calculated the last digit, then you don't need to use this loop anymore, you can just break out of it. So that's why this break condition. Look at the other condition we have after this one, which is if map of s of I minus 1 is less than map of s of I, sum minus equals to map of s of I minus 1. Okay, let's decode this thing. This is the main thing where the condition we used right there will be coming into play. Basically, map of s of I minus 1 is less than or equal to map of s of I. Basically what happened here is s of I minus 1. Here we have I minus 1 will be I minus 1. If we take another number variable just for reference, it will be 0. So we're checking the 0th position, which means we're checking the leftmost digit, left digit to this particular x, which is I. We're checking if this particular digit is less than this one, which is going to subtract it, right? Which in this case it is 1. The map of it will be 1. So yes, 10 is greater than 1 according to this condition, I minus 1. So s of I minus 1, which is x and I, and map of s of I will be 10, map of s of I minus 1 will be 1, and 1 is less than 10, thus sum will be updated to 10, which is map of s of I, sum minus equals to map of s of I minus 1, which is 1. So the value will be 9. So the value of sum now is 9. And decrease the pointer by 1, which is now the value of I is 0. Well, I can get out this if condition, and there's another one. There's another I minus 1 equals to 1. So I will be equal to minus 1. So now we'll get to this while loop again, and we'll see that I is not less than or equal, greater than or equal to 0. I is minus 1 now. So what it'll basically do is this while loop has terminated. When the while loop has terminated, let's look at the sum. This is where the sum is 9. Just return 9 sum. Just return the sum now, because we have actually found the sum of the particular Roman numeral, which is 9, is I and X. So basically what you have done is we've gone from the back, the left rightmost value of the Roman numeral to the leftmost value, and we have checked whether the particular left value of the Roman, each and every I, basically what we checked is whether S of I minus 1 of each and every digit for all S of I, whether it's greater or less than a particular value of I. Based on a particular condition, we have used this thing. Basically we are either adding the particular value or subtracting it from the thing, and it's pretty efficient. But let's look at the problems here. This code, this particular pseudo code that I have written is mostly Python, so you can basically write this entire code in Python and it will work. The problem here is the first one, which is we have to use this condition all the time. If I is equal to 0, break. So for example, if the number was not ix, if it was something like x v I I I, so it was x v I. What we do is, for each and every iteration of I, we'll use this condition. We have to check it, even though this condition is only required at the end, whether it is at the end or not. If we calculate the end value x, we need this condition. We don't need to go any further and we can break it, but we need to use this condition all the time. And what if we don't use it? What if we don't use this condition is, if I is not equal to 0, if I is equal to 0, what happens is S of I minus 1 will not be there, right? Because S of I minus 1 is, will be minus 1, and S of I minus 1 doesn't exist. So Python will raise an error, out of bound index error 1, which will be a problematic situation here, which is why we can't take this thing out. We need to use this code, but what it will do is we have to iterate this thing all the time, which means if I is equal to 0, break will be iterated for 1, 2, 3, 4. So for all these 4 times it will be iterated, even though it's not necessary to do so. What we could do is we could optimize this code by not changing this particular code in any way. The basic intuition is still the same. We use x and I and we go backwards and we check whether it's greater or not. Based on that, we'll subtract or divide, subtract or add. But here what we'll do is, rather than doing this, we'll tweak the code. Now the basic thing is that it's still O of n. The time complexity of this code is O of n. In the worst case, it will be O of n. But the problem is, if we neglect the asymptomatic notation for a second, if we just ignore O of n for a second, what it will do is, this particular condition will take unit 1 time. It will take 1 unit of time in order to be executed, as every condition should. And for all these ones, it will take 4 units of time. Now imagine if the Roman numeral was 28 or 100 numerals, there are 100 digits or 100 bits for each and every Roman value of the particular Roman numeral. It will take 100 times, it will take 100 units to process the particular if condition. Now it's not necessary. Leetcode will still accept this particular solution. It will be highly efficient. It's O of n, as I said, since asymptomatically it's still O of n, but we can improve it more if we want to. We can improve this code so that we don't need this condition at all. We completely cut this condition off, thus saving us 100 units of time if it could. And rather than looking at time complexity as O of n, we can just look at it as each and every particular condition being taken time in this while loop, we can decrease that. We can decrease the time by a little bit, which is significant sometimes. So let's look at the other code, which is much more efficient than this one. So this is a new and much more optimized code when it comes to coding competitions and all that. Since in coding competitions we don't have exact asymptomatic notations of time complexities, we have an exact time which you have to meet below or at least to that particular point, so in order to be accepted by the particular contest holder. So let's look at this code first. What we did is we took we have like one. So what we did here is we have three variables, which is answer, Rome, and I. In this case, Rome is a particular string, which is the inverted string of our particular given problem statement. In this case, xiv is a particular Roman numeral, which we all know is 14. But let's see how this algorithm is used to give that particular conclusion. This one first, what we do is we'll reverse the particular string. We inverted the string in Python. We use s of 2 colons minus 1 in order to invert the particular given string, which will give us v, I, and x. The particular which will give us v, I, and x. So what we'll do is initialize the answer to 0, which is our answer, and we'll first what we'll do is answer plus equals to dictionary of Rome of 0. Dictionary being the particular hash map that we will use. I'm not going to write it here again. But what we'll do is we'll calculate the Rome of 0 for the answer. So let's look at this one. We have Vix as Rome. The way indices values are 0, 1, and 2. So we're going to calculate the value of Rome of 0, which will correspond to 5, right? So the value is 5. So here we'll add the answer value is 5. So now we add the answer value as 5. So the value of answer is 5 here. So basically what you have done here is we got the value of answer as 5. So we basically added the leftmost value, in this case the rightmost value of the particular string to initially get the particular value of the rightmost value of it. So what you're basically doing is we'll always calculate the rightmost value of the particular string and we'll keep it in the answer before we get into the particular loop, so that it will make a code easier. As we get into it, we'll look at it, and it's not going to work, it's not going to fail for a single case. If we give x for s, the reverse value will also be x, and we can just calculate this, which will be 10, and this won't even get into this particular loop and return the value of 10. So this will work all the time, so we don't have to worry about it. So we can add the value of this, we'll get 5. Now we'll get into the for loop. For loop will give us from the range of 1 to length of Rome, because we already calculate the value of 0, right? For I of 0 we already calculate the value here, so you'll only calculate from 1 to, in this case, is 3, which won't include 3. So we'll calculate the value for I is equals to 1 and 2 only. So first we're at I is equals to 1. So let's look at it. Here we only have two conditions, which is if dictionary of Rome of I is greater than or equal to dictionary of Rome of I minus 1, we'll add the answer, we'll add the dictionary of Rome of I to the answer. If not, then subtract it. It's a pretty easy one. Let's look at it now. Basically, we have reversed the string and we're going from the rightmost to the leftmost as we have intuited before, and we're using the same condition as the previous code, but the thing we have changed here is I already added the value of v here, so we don't need to check whether this loop is going to terminate. We don't have if I is equals to 0 again. We want to check whether it's going to terminate or not. This for loop will take care of the termination part, where it's going to terminate or not. What happens here is Rome of I of minus 1 will always exist because I is equals to 1, so I will always be here. Since we already added a particular value here, we'll always have a value preceding it, so I of minus 1 will always be there. We don't need to check whether I of minus 1 is greater than or equal to 0 of I. We don't have, so basically what happens here is we don't need if I is greater than 0 condition, because I minus 1 will always exist for any value of a particular Roman numeral. So what happens here is, for I, we are given room of I is 1, in this case, I which is 1. So if it is greater than or equals to room of I minus 1, add the answer. So we already know the room of I minus 1 is 5. And this is not true. In this case, if we add it, what will happen is 1 is greater than 5 is false. This is the condition which we'll get here. So dictionary of room of I is 1 and dictionary of room of I minus 1 is 5. This condition is false. So what will happen is else condition will be activated, which will give us answer minus 1, minus of dictionary of room of I, which means that for the answer we'll just subtract 1, which is the room of I, this current one where I is. So this one is also taken care of. We'll get the answer as 4. So go to the loop again. I has been finished. We'll go to I is equals to 2 now, which is this particular value 2. It's 2. So in this one we can see x, the value of x is 10. Now let's look at it. Dictionary of room of I is greater than or equal to dictionary of room of I minus 1. I minus 1 being, in this case, room of I minus 1 is 1 and room of I is 10. And yes, this condition will be satisfied. So what happens is we'll add the answer to dictionary of room of I. We'll add the answer to dictionary of room of I. What happens here is we get the value as 14. So I of 2 is also been done. So since we have covered the range, we already covered the range of 1, I of I is equals to 1 and I is equals to 2. So we'll get out of the loop and the answer left is 14, which you can just return here. So basically this is the much. So as we've seen here, we can already predetermine a value at the beginning of the particular, before you even start the loop, in order to get the value of 5, so that we don't need to check for any particular edge cases where I can't be there or I doesn't exist, because in the for loop will take care of the I value in this range, and I minus 1 will always be present for any value of any string is given, because we already calculate this value, and if the value of length of s is 1, then this condition won't even come into play. So for any value of this thing, whether the length of s is 1 or not equals to 1, then this condition will be activated and I minus 1 will always exist. So we don't have any logic gaps here. So this code works much better because there are only 2 conditions here. This will always be necessary, this will always be required. In this case, 5, when we calculate the value of 5, which is Vix, let's write this thing again. So for V, I and X, we already calculated the value of V. So for I, we should check whether V is greater than or less than equal to I. We always need to check it, which is the exact point of the intuition we need to be doing. So no matter what, this condition will always be activated once, and it should be activated once in order to get the value. In this case 5, no, it's greater, so it's minus 1, and it's greater, so plus 2. So you always need to check whether it's there or not. That's the basic intuition. That's why this code is much more efficient, because the particular if conditions and else conditions here are necessary and they are not redundant. This is the final intuition that I believe is pretty efficient. So let's look at the code now. I'll write you down the entire code and you can copy it down if you write. So this is the final code here. It's basically similar to the code that we are written in intuition number 2. The only difference is here I didn't mention dictionary as again. You can just write it down, all the particular table, you can fill it up here, and as the particular values of the particular, if you can just fill this table here and that'll get you what you want. So before you write this code down, a pro tip, you can remove the length of Rome here and instead add a variable which is length is equals to 0, len of Rome. You just write you can write it like this, even though both are the same thing. What happens here is when you write len of Rome, this particular len of Rome is a function, right? It's a function that len of Rome is a function that gives you the length of a particular string or an array. What happens in for loop is when you keep calculating when I keeps iterating to a loop again and again, you have to calculate len of a if len of Rome is here again and again, which could take a while. And as I said, if it takes 1 unit of time, it could take in this case 4 units. If the length of the string was 4, it will take 4 units of time and stuff like that. So rather than that, if you just assign to a variable before, what happens here is you can just write length and it doesn't calculate anything. It just checks with the value of length, which is in this case could be 4 or 3, and it will just loop it till that particular value. So this is a much more efficient code. So at the end, if you'll give the return this answer, you'll get the integer to the Roman numeral. And all you have to check here is to make sure that there are not any functions in this loop. Try to avoid any functions inside this loop, as many functions as possible, and try to put as many variables here as possible, as you have seen in length. In case of length, and in this case we only have 2 conditions. So we only have 2 conditions in this for loop from the 4 conditions we had before. So we have to make sure that you take care of that.